Hello, my name is Dana Bernhardt, and I am the team lead for Project 19027. This is the Craig Berg Design Day video presentation for Roche's physical user interface for digital pathology. Here is a picture of our digital poster, and here's a picture of our team with our Roche polos. Below the paragraph description are a series of images to demonstrate the brainstorming progression we had throughout the year. Our team was tasked to create a device mimicking a compound microscope in order to bridge the gap between digital pathology and traditional pathology. We initially created a similar looking device, but with a trackpad on top in place of the eyepiece and oculars. This provided the user the option of either a trackpad or the traditional knob seen on a microscope. Later, the arm was removed in order to increase the stability of the device, and the trackpad was moved out front. Here is a list of our system requirements in case you would like to pause here to read this section. And next, my colleague Claudia will go into more depth on the next sections of this poster.
Hello everyone, my name is Claudia Carlos. I'm a system engineering student. And since the beginning of this project, our goal was to build and deliver a product that would ultimately meet our customer needs. In order to decide which design features would best satisfy our customer and also ensure our product would be accepted on the market, we surveyed 25 pathologists and other slide readers. Most of the questions on the survey were related to the device main functions, the panning and the magnification. And with this survey, we wanted to know how receptive our design ideas were. This slide shows the results we selected from the survey and implemented on our design. The first two graphics are related to the magnification setting preferences, and the last one is related to the panning of the image using a trackpad similar to the one that we find on a laptop. This is the POI system block diagram. It shows all the components of our system and also show how these components are connected to each other. Outside of the dashed lines, we have the computer from the RTD that contains the OpenSea Dragon software that will interface with our Arduino code. This computer will be connected to our device using a micro USB.
Our first system analysis needed to validate that the slide image would move in a similar fashion and speed as a compound microscope. To accomplish this, we created an analysis experiment using measurements from multiple laboratory microscopes. We took some practical measurements and converted them into a ratio that compared knob turn angle to image pixel translation. Along with mimicking the translation of slides, we also needed to verify the magnification settings matched a compound microscope. To ensure that the image magnification would increase linearly, we used a professional compound microscope with an attached camera display to measure the viewing size of a cell and match it with our software's display. With our analysis, we could confirm the software would be able to jump to magnification levels familiar to professionals per the request. The user can also choose to operate a fine magnification knob to view images at magnifications between standard settings. Here, our functional goal was to have a design that is both portable and stable. To define stability, we claimed that our device shall withstand tipping or slipping forces of under 10 newtons. To verify our design, we used SOLIDWORKS' center of mass function and MATLAB computations to generate the free body diagram shown here. All the model predictions exceeded the requirement of withstanding 10 newtons. Our next presenter will be Madeline, and she'll be talking about our software design.
Hello, my name is Madeline Armstrong, and I will be discussing the software and electrical setup of the PUI. The CPU of our system is an Arduino Leonardo, which, together with the panning and magnification subsystems, acts as a human interface device to control the digital image. The Arduino runs on a regulated 5-volt power supply through the micro USB that connects the system to a computer. Each knob for the XY panning and magnification subassemblies uses a rotary encoder to accurately receive data when a user turns the knob in either direction. The system has 2 knobs for X and Y axis panning and 2 knobs for coarse and fine magnification. The PS2 interface of the trackpad is converted to Arduino-friendly digital pins via an adapter. The software package, called OSD Viewer, is a C#.NET web application that imports a scanned BIF file into OpenSea Dragon, an open-source JavaScript viewer for high-resolution images. An Arduino program written in C++ translates user inputs into the appropriate commands, which are then sent to the C# application via serial communication. The sensitivities of the knob and trackpad can be easily adjusted in the code. Next, Daniel will talk about the PUI's mechanical assembly.
Hello, my name is Daniel June, and I am the mechanical engineer for the project. So our design is meant to mimic that of traditional microscopes, dimensions and controls wise, that are currently found in laboratories today, with the added benefit of a trackpad that allows for a secondary means of X and Y panning. The trackpad is set at 5 degrees offset towards the user in order to reduce user fatigue. The knobs are stacked, which is commonly found on both panning and magnification knobs and on microscopes, which is achieved by using a gear train which allows for 2 different rotary encoders to be driven. The top case once removed, allows for access to the majority of components inside of the system, with the exception of the gears, which have their own covers which can be removed by a couple of bolts. Next, Matt will be talking about the manufacturing process of our project.
In our first semester, we got off to a quick start developing a prototype design and assessing the functionality of our subassemblies. We acquired all of our operational parts and designed a frame to contain them. As a part of our risk mitigation plan, the trackpad was the first subassembly to be prototyped since it had the highest risk. Unfortunately, our ideal trackpad had faulty connections and could not operate at an effective rate, but we were prepared with a second trackpad from a different manufacturer. As we finalized our design and began systems testing, a large part of our March to April schedule depended on the lead time for our machine parts, which we had anticipated to be 1 to 4 weeks. Around mid-March, the COVID-19 pandemic hit and made producing our parts much more difficult to our team. To mitigate this risk, we planned to switch to printing our parts. However, by the time we made the switch and placed the request, the quarantine restrictions and high workload at Roche had forced them to cancel all students' project manufacturing. To accompany this pandemic dilemma, most of our final acceptance tests had been planned to be performed at Roche or in a university lab setting. With their closure, this prevented us from performing our final acceptance tests within the accuracy of our specified tolerances. With our vision so close yet unobtainable, our final push of the semester has been oriented towards improving drawings, specifications, and remote demonstrations to ensure the eventual completion of our system. We've created and demonstrated the fully functional wiring and software capabilities of our subassemblies with our predicted analysis values, and we have written supporting documents to aid in the assembly and operation of the physical user interface in the events the parts are completed.
While we were unable to complete the fabrication process for our project due to the current ongoing pandemic, we have still learned much from this experience.